Alright, this lesson in Chem 30 today is about carboxylic acids. So this is the next functional group we are studying. And for carboxylic acids, note that we have a carbo, and so we have a carbonyl group. That is the C doubly bonded to the O. But we also have a hydroxyl group, and that's the OH, if you recall. So when we have these two things together, carbonyl and hydroxyl, it's carboxyl. Okay? And they're always acids, so carboxylic acids are what we're going to be studying here today. So we want to note a couple things in the structure of the formula. Again, this carbonyl group and a hydroxyl group. Just a note over here that in the structural formula here, the C is doubly bonded to an O, and then it's singly bonded to a different oxygen. So it's not drawn like this right here. Structural formula would not be drawn just like this. The C is doubly bonded to the O here, but the other oxygen is not bonded to this oxygen, so you can't draw it structurally like this. What we will see, though, is that you can write it, and it's on the next slide. When we write the formula, you do write it like COOH. So that is okay, but you have to remember that structurally this is not how it goes. Okay? It looks like this. So if we just go back to the naming here, okay, what you do is you look at the carbon chain and you take off the ane and you add anoic acid. So if you see here, the one carbon would be methane, and because we have a carboxyl group right here attached to it, it's methanoic acid. Now for these ones there's a lot of common names. You do not have to memorize all the common names, but methanoic acid right here is how we would name that. Alright, so the condensed formula again is the COOH, but please don't be fooled. These O's are not bonded to each other. This one right here, we have two carbons, so that's ethane. That would be ethane, right? Except we have the carboxyl group right here, and so it's ethanoic acid. Ethanoic acid. And this is acetic acid in vinegar and stuff like that. It's the formula for acetic acid. We take a look at properties of carboxylic acids. They are polar as well. A lot of these functional groups are polar molecules, right? Polar and reactive. It's fairly common. Those that dissolve in water ionize weakly to produce hydronium ions. So most of these carboxylic acid compounds dissolve in water to produce hydronium, or they release their hydrogen, and so that's why most of them are called acids. Okay, so the carboxylic acids produce hydronium ions. We'll talk more about this in the acid-base unit, but just suffice to say that they make acidic solutions, so they dissolve in water, and they ionize quite readily. So because they ionize in water, soluble carboxylic acids have the common characteristic of acids, like turning blue litmus paper red and having a sour taste. You don't have to copy that down. We will discuss this, as I think you might have, well, maybe you haven't run across much of this litmus paper. Have you heard of litmus paper? Yeah, in bio maybe, and in other chemistry lessons, but that's how you test for acid or base, and blue litmus paper turning red is a test for acid. It's also sour. Some additional functional groups such as hydroxyl groups, as in lactic acid found in yogurt. So you've heard of lactic acid, right? So this is a carboxylic acid, lactic acid. Lactic acid is also the acid that builds up in your muscles, sort of as a byproduct of exercise. And the reason why you're sore the next day if you work out really hard, the reason why you're sore is this buildup of lactic acid in your muscle. And so if you work out after a game or a practice or some kind of workout, you need to cool down, to cool down. That's not just a temperature thing. It also kind of works out, it kind of flushes out a little bit this lactic acid, so you're not as sore the next day. Seeing as we were just talking about Cornell and my time at Cornell, one of the things that I used to do after every practice and every game was skip rope. And it sounds a little funny, but That was one of the things you could get on the bike or you could skip rope or something like that. So I just went and just skipped rope for 5 or 10 minutes, and that kind of worked out the lactic acid, so I wasn't sore the next day. So those of you that are athletes, you can remember that the cool down is not just for you to catch your breath. It's not just for you to cool off. It's also for your muscles. So you should do a little bit of light repetitive work for 5 or 10 minutes afterwards, just to work out this lactic acid. Typically, these acids are more soluble in water and often more acidic than acids with only a carboxyl group. So again, that's moderately important, just some information. So carboxylic acids. Some organic compounds that are derived from carboxylic acids. Several classes of organic compounds have structures in which the hydrogen of the hydroxyl group of a carboxylic acid is replaced by a different atom or group of atoms. The two most common classes are esters and amides. So you kind of see, I guess it's nice to see this on the same page, but do you see how the next group we're going to study, which is esters, has a carbonyl group, and then it has what looks to be, that was a hydroxyl group. The H has now been replaced with something. And so that makes it a different group. So carboxylic acids, this hydrogen, which is released readily in solution, right, to make the H plus ions in solution to make an acid, there's kind of an open spot for something else to bond here. So there are derivatives of carboxylic acids. So if you want to write that down, the hydrogen is replaced, okay, in the hydroxyl group to make other functional group like esters and amides. So let's talk about esters. Okay, ester, this is spelled a little bit different than Esther in the Bible there, E-S-T-H, or the ester, the name, but it's pronounced the same. An ester is an organic group, as we just talked about, where the carboxyl group, the hydrogen has been replaced. Okay, hydrogen is replaced by some kind of alkyl group. So notice that this is an R here. An alkyl group is some kind of carbon chain of some sort, right? So an ester is very similar to carboxylic acid, but the H is replaced with an alkyl group. All right, so if we're looking at naming esters, and again, here you have a carbonyl, an oxygen, and then a carbon chain. To name esters, what we do is we write the name of the alkyl group, so followed by the name of the acid with the ic acid replaced by 8. All right, so let's just take a look at this one here. We have right here, there's 2 carbons here, that's F, and we have 3 carbons over here, that's prop, right? So we name the chain that is part of this oxygen bonding. We name that chain is the ethanoic part, and here's the ester group, well, right? So we name this group first. So name the alkyl group first. So this is 1, 2, 3, meth, F, prop. So we name this one first, number 1, and then we name this chain second, and we take off the ic acid from the carboxylic acid and we replace it with 8. So it's propyl, that's the alkyl group, propyl, F for the carbon chain that's kind of underneath the O there, attached to the oxygens, and then FNO8, propyl ethanoate, or ethanoate. And a common name is propyl acetate. So once again, here's number 1. You take a look at this chain that's on to this ester group, and then you name the parent chain and the O8. The 8 is at the end there. Technically leave the O right there from the oic acid, but it's ethano8. All right, so if we have a little practice naming some esters. Let's take a look at this one first, right here. You see that we have an ester because we have this right here, right? You have the carbonyl group here, and you have, it's attached to a, oh, I'm missing an O actually, aren't I? Okay, there we go. So here's our, yeah, this is the group here, right here, with the O and the C, right? So that's an ester. Yeah, that should be a 3, thanks. I was going to go further, but 3. All right, so let's see, CH3, CH3, 1, 2, 3, 4, yeah. Okay, so we should be good here. So let's name this ester. If I can get rid of that. There we go. So what are we looking for first? We're looking at this group first. And so how many carbons are there? 2, so that's a what? Yeah, that's ethyl. So this is the one you name first. Then you go over here and you count the carbons. Do you count this carbon under the O or not? Let's go back. Yep. Count the carbon under the O as part of that chain. Because you want to name the you just named this group first. Why? I'm not really sure why, because this is the chain that makes it an ester. So yeah, because this chain right here, this could be part of a carboxylic acid or a ketone or something like that. So this is the one you name first because well, that's just sort of the rules, I guess. I can't really tell you any more than that why, but this is what makes an ester, this bond right here to another carbon group. So I name that one first. So then they go back to what would be sort of the, you might consider, I guess you're considering this the parent chain, but so 1, 2, 3, 4, what's that? That's bute. Good. So what do I put after bute? Yeah, NO8. Very good. So we have the ethyl, matches with this group right here. We have the bute, which is the 4-carbon chain there. And then we have the O8, I guess, is because it's an ester. Okay, there's example 2. We'll go ahead and name that, and we'll talk about that in a second. Okay, so here's the name for this particular substance right here. We have the methyl group we name first, and then we have 1, 2, 3, 4, 5 carbons, so that's pentane, and because it's an ester here, it's O8 at the end, methyl pentanoate. So I want you to practice drawing these ones, propyl hexanoate and octyl butanoate. Propyl hexanoate and octyl butanoate. Okay, let me know if you agree with that first one there. Okay, I had to move it down there so I had enough room. But you guys agree with that one? Okay, so the first one, the propyl, is meth F prop, so that's attached to the O over here. And hexane is 6. 1, 2, 3, 4, 5, 6 carbons there in the chain, and O8. So propyl hexanoate looks like this. And octyl, 8 carbons there. Butane, so that's, was that 4 here? And that's octyl butanoate. Agree? Any questions? Pretty straightforward. Esters are polar molecules. Again, polar. Many are volatile, but many are also sweet smelling. Natural kinds of esters are found in natural fragrances and flavors of flowers and fruits. Flavors of flowers, okay. Not sure how many of you are eating flowers, but fragrances of flowers and flavors of fruits are often due to the ester type organic molecule. So natural flavors, such as apple or banana, result from the mixture of many different organic molecules, including esters. Some of these flavors can be imitated by a single ester structure. Consequently, esters are manufactured for use as flavors in many foods, beverages, and fragrances in candles, perfumes, and other scented items. So when we're talking about synthetic flavors or synthetic fragrances, because esters are often found in the natural, fruits or flowers, but it's a rather complicated mixture, maybe in a fruit or flower. When they try and imitate the fragrance or the taste, they'll start with an ester and they'll try and find an easily manufactured ester that is similar. And sometimes they do pretty well, right, to get the banana flavor or the strawberry flavor, right, or the perfume that smells like whatever, lilies or tulips, or I don't know what kind of perfume you want. But anyways, so esters, a single ester structure can be manufactured for use as flavors or fragrances. So esters are responsible for the flavors and aromas of many fruits. The aroma of strawberries is due in part to methyl hexanoate. Ethyl butanoate contributes to the aroma of pineapple. Most natural aromas and flavors are mixtures of esters, aldehydes, and alcohols. So the organic molecules and functional groups we've been studying are a complicated mixture for getting the smells that and tastes that we experience in nature. So methyl hexanoate is connected to strawberries. You might want to write that down. The flavors and aromas of fruits, of strawberries, methyl hexanoate. Next time you're drinking a strawberry milkshake, you can sniff it and go, oh, methyl hexanoate in the evening. Just really gets me going. I love it. So that's the way you creep out your friends and appear, ostensibly nerdy. But anyways, next time you see a pineapple, you can utter ethyl butanoate too, and you'll look really smart. Sound really smart. May not have as many friends afterwards, but I don't know. All right, amides is our next group that we're going to study, and I believe this is the last one that we're going to study in this section. Amides, it's an organic compound in which the OH group, the hydroxyl group of the carboxylic acid, so as we mentioned, amides and esters come from carboxylic acids. So the O and the H are replaced by a nitrogen atom bonded to something else. So the big thing is, again, amines was nitrogen, right? Amides, still nitrogen. And the general formula looks like this. So here's that carbonyl group, C doubly bonded to O. And then over here, we don't have an O, we have now an N. Okay? And of course, the N can be bonded to whatever. But this is the big thing here. This is amide. So if we go back to the amines just really quickly, remember amines had nitrogen as well, but it was an NH2 group attached to a chain or an alkyl or an aryl group, so NH2. Now notice that there was no oxygen, no doubly bonded to oxygen, so that's the big difference. Amines, no oxygen there, and amides, right? Amides have the oxygen as well as the nitrogen. All right, so when we're naming, okay, write the names of the alkane with the same number of carbon atoms, and then replace the final E with amide. Pretty easy. You don't have to really worry about, really you're just focusing on the carbon chain here, and then if it's an N, H2, or N, H, and then another carbon chain or whatever, it's an amide. So this is just ethan amide. Ethanamide. Or we call this acetamide, that's the common name. So eth, meth, eth, ethanamide. Properties and uses of amides. The amide functional group is found repeated many times in natural proteins and some synthetic materials. For example, acetaminophen, you guys all know what that is? Tylenol, yeah, it's the actual chemical name for the substance. That Tylenol is kind of the company name, we kind of go by that, but acetaminophen, you'll see if you get the no-name, Tylenol, if you're looking for Tylenol and you see acetaminophen and it's cheaper because it's a no-name brand or something like that, you can say, hey, I know that's Tylenol. Just like ibuprofen is, you know what that is? Ibuprofen is Advil, yeah, Advil. Okay, so for example, acetaminophen has an amide group connected to a carbonyl group and an aromatic group. So what you see here is you see the N connected to the C, which is doubly bonded to the O. So that means we have an amide. Okay, so there's two carbons here. And the N is attached to an aromatic group, so that looks like a benzene, right? Benzene ring, right? And here we've got the hydroxyl group over here as well. This happens to be acetaminophen. Now the simple naming that we just talked about here, right? Just with the I, that's for I think that's just for NH2. You would have to name it a little bit differently for this, which I don't think we'll get into here in this course, but just out of curiosity, that's the acetaminophen molecule. Another important amide is caramide, or common name urea. It's an end product in the breakdown of proteins in mammals. So that's another important amide, urea. Because of the high nitrogen content of urea, and because it's easily converted to ammonia, that's NH3, in the soil, urea is a common commercial fertilizer. Okay, so we're talking about natural breakdown in mammals, all right, comes into the soil, okay, and so fertilizers are made with the same group. So you kind of see how organic chemistry is using, we study natural things, okay, so when animals, they excrete their waste, and we realize that, hey, that's good for the soil, it makes things grow really well. Well, what's in there that makes the soil, the soil's got some nitrogen in it, this has got a lot of nitrogen in it, so we kind of get the idea in our head that, hey, let's try and make fertilizer so we can, we don't have to get a bunch of cattle and goats to poop all over the lawn to make it good. We can actually add some fertilizer that's easier to buy, right? So this is sort of how the study of chemistry, drives industry and drives new products and that sort of thing. So urea is also used as a protein supplement for cattle and sheep. All right, so it's in naturally in proteins. Acetaminophen is a common amide, and urea, and also it's used in making fertilizer. Okay, so if you have down those properties and uses of amides, that's good. All right, so that concludes the functional groups that we're going to study here. I did put this little slide up here, leading families of organic compounds. Now, I think this is I think this is all of them, but I just clipped this on, so I just thought it's kind of nice to have everything in one spot. So let's just go over this real quick, see if there's anything that's missing on this list, or anything extra. But a hydrocarbon is simply carbon and hydrogen molecule. Methane is a simple example here. And so we've got carbon attached to hydrogens. If you put an OH, a hydroxyl group, onto a carbon chain, you've got now an alcohol. An aldehyde here has this C doubly bonded to O. Okay, this is an acid. It's a carboxylic acid, right? We talked about. So you can write carboxylic acid here. I don't know if you don't have to write this down, but if you are, it's carboxylic acid. We talked about an ester as well here. So C doubly bonded to O, bonded to another oxygen and a carbon group, ester. This is an ether, COC, ether. The ketone here is carbon, carbon, carbon with the this carbonyl group here. Different than the aldehyde, there's H's here, this is in the carbon chain. An amide with an NH2 onto a carbon, amine, and amide is an NH2 onto a carbonyl group here, C doubly bonded to O. So is there any on there that we studied that is not on this group? Anything we need to add here? Yeah, halocarbon, that's right, we talked about halocarbons initially, and that's where, yeah, let's put that on there. So halocarbon, and what's that? That's where we have a halogen connected to a carbon, right? So something like this. Right? We have the halogen there. So fluoromethane CH3F is the formula for that. Yep, so I think that encompasses everything we've studied there. And again, that's on your sheet, that handout that I gave you. First, all those should be on there with examples, with structures, so it should even be better than this one, the sheet that I gave you. But yeah, that's a little bit of everything right there.